Section: Introduction. In this section, we discuss how large language models, LLMs, have significantly improved their ability to tackle coding, mathematics, and reasoning tasks over recent years. A key factor driving these advancements has been the scaling up of model training. By investing in larger models, more extensive pre-training datasets, and thorough post-training processes, like gathering human preference labels, we have developed highly capable generalist systems. However, we have noticed that there has been relatively little investment in increasing the computational resources used during inference. While larger models do require more computational power for inference compared to smaller ones, techniques such as chain-of-thought prompting can enhance the quality of answers, albeit at the expense of longer and more resource-intensive outputs. Despite this, users and developers often limit models to making just one attempt at solving a problem. In our work, we explore the concept of repeated sampling as a way to scale inference computation and enhance the reasoning performance of LLMs. The effectiveness of repeated sampling hinges on two main factors: coverage, which refers to the proportion of problems we can solve with any of the generated samples as we increase the number of samples, and precision, which concerns our ability to identify correct samples when we need to choose a final answer from the generated collection. If we have unlimited attempts, any model that gives a non-zero probability to every possible sequence can achieve perfect coverage. However, repeated sampling is only practical if we can enhance coverage within a reasonable budget. Additionally, without a method to differentiate between samples, the usefulness of repeated sampling is limited. Previous research has shown promising results in both areas, indicating that repeated sampling can improve performance in math, coding, and puzzle-solving tasks. For instance, AlphaCode, a leading system for competitive programming, demonstrates that performance continues to rise with up to 1 million samples per problem. In our findings, we show that repeated sampling is an effective strategy for boosting coverage across various tasks, models, and sample budgets. For example, when we tackle programming problems from code contests using the Gemma 2B model, we see coverage increase by over 300 times as we raise the number of samples, from just 0.02% with one attempt to 7.1% with 10,000 attempts. Interestingly, we observe that the relationship between the logarithm of coverage and the number of samples often resembles a power law. With models like Llama 3 and Gemma, coverage tends to grow almost log linearly with the number of samples across several orders of magnitude. In scenarios where a model's solutions can be automatically verified, such as with proof checkers or unit tests, these increases in coverage directly lead to better task performance. For instance, when we apply repeated sampling to competitive programming and writing lean proofs, models like Llama 3-8B Instruct can outperform much stronger models like GPT-4o when we allow multiple attempts. This ability to enhance weaker models also applies to the challenging SWE Benchlight dataset, which consists of real-life GitHub issues. The current best performance from a single attempt, achieved by a combination of GPT-4o and Claude 3.5 Sonnet models, is 43%. When we give DeepSeek Coder v2 Instruct just one attempt, it only solves 15.9% of the problems. However, by increasing the number of attempts to 250, we boost the solved problems to 56%, surpassing the single attempt best by 13%. In addition to enhancing model performance, repeated sampling offers a new way to reduce inference costs for LLMs. When we keep the total number of inference operations constant, we find that for some datasets, like math, we can maximize coverage by using a smaller model with more attempts, while for others, like code contests, a larger model is more effective. We also compare the costs of using APIs from DeepSeek v2 Coder Instruct, GPT-4o, and Claude Sonnet 3.5 in the context of solving SWE Benchlight issues. By maintaining a consistent agent framework, we find that sampling 5 times from the less powerful and cheaper DeepSeek model solves more issues than making single attempts with Claude or GPT, all while being over 3 times cheaper. Finally, in the context of math word problems, where answers cannot be automatically verified, we identify a significant gap between coverage and the performance of common methods for selecting a final answer. For instance, when solving math problems with Llama 3 to 8b instruct, coverage rises from 79.8% with 100 samples to 95.3% with 10,000 samples. In contrast, methods like majority voting and reward models plateau at a lower sample budget, only increasing from 38.7% to 39.8% over the same range. These findings underscore that developing robust verification methods remains a challenge. In summary, we have observed that scaling inference computation through repeated sampling leads to substantial improvements in coverage across various tasks, models, and sample budgets. This approach allows us to amplify the performance of weaker models with many samples, enabling them to outperform single attempts from more capable models. Notably, we have been able to solve 56% of issues from SWE Benchlight by sampling 250 times from DeepSeek V2 Coder Instruct, exceeding the single-attempt best of 43%. We also demonstrate that the relationship between coverage and the number of samples can often be modeled using a power law, suggesting a scaling law for inference time computation. In areas without automatic verifiers, we find that common verification methods like majority voting and reward model scoring plateau after about 100 samples, leading to a widening gap between the performance of these methods and the upper limit of coverage. Section Summary. In this section, we explore how repeated sampling can significantly enhance the reasoning performance of large language models, LLMs, by improving coverage and precision across various tasks and models. Our findings indicate that by increasing the number of attempts, we can amplify the capabilities of weaker models, achieving better results than single attempts from stronger models, while also providing insights into the cost-effectiveness of inference compute. Section: Scaling repeated sampling. In this section, we focus on tasks where we determine if a solution is correct or not, which we refer to as pass-fail tasks. The main measure we are interested in is the success rate, which is the proportion of problems we can solve. By using repeated sampling, we set up a scenario where our model can produce multiple candidate solutions for each problem. This success rate is affected by two factors: our ability to generate correct solutions for a variety of problems, known as coverage, and our ability to identify these correct solutions, referred to as precision. The challenge of ensuring precision depends on the tools we have for verifying the samples. For instance, when we prove formal statements in Lean, proof checkers can quickly confirm if a candidate solution is correct. Similarly, we can use unit tests to verify solutions for coding tasks. In these situations, precision is managed automatically, so enhancing coverage leads to higher success rates. On the other hand, the tools we have for verifying solutions to math word problems from datasets like GSM-8K and math are limited. This limitation requires us to use additional verification methods to choose a single final answer from many potentially conflicting samples. We examine 5 specific tasks. 1. GSM-8K. This is a dataset of grade school level math word problems, and we evaluate a random selection of 128 problems from its test set. 2. Math. This dataset contains math word problems that are generally more challenging than those in GSM-8K, and we also evaluate 128 random problems from its test set. 3. Mini F2F Math. This dataset consists of math problems that have been formalized into proof-checking languages. We use Lean 4 for this and evaluate 130 test problems that are formalized from the math dataset. 4. Code contests. This dataset includes competitive programming problems, each with a text description and a set of input-output test cases, which are hidden from the model, to verify the correctness of a candidate solution. We require models to write their solutions in Python 3.5. SWE Benchlight. This dataset features real-world GitHub issues, where each problem includes a description and a snapshot of a code repository. To solve these problems, models must edit files in the codebase, and in the light subset we use, only one file needs to be changed. Candidate solutions can be automatically verified using the repository's unit tests. Among these tasks, Mini F2F Math, code contests, and SWE Benchlight have automatic verification tools, such as the Lean4 Proof Checker, test cases, and unit test suites. We start by exploring how repeated sampling enhances model coverage. Improvements in coverage are directly linked to increased success rates for tasks with automatic verifiers, and in general, they provide an upper limit on the success rate. In coding contexts, we define coverage similarly to the commonly used pass at K metric, where K represents the number of samples per problem. We apply this metric directly when evaluating code contests and SWE Benchlight. For Mini F2F, we define a pass based on the Lean4 Proof Checker. For GSM 8K and Math, coverage is determined by using an Oracle verifier that checks if any sample produces the correct final answer. To reduce variability in our coverage calculations, we use an unbiased estimation formula. In each experiment, we first generate a set number of samples for each problem and count how many of those samples are correct. We then calculate the pass at K scores for each relevant K value. Next, we establish that repeated sampling effectively improves coverage across various tasks and sample budgets. We evaluate the Llama 3 to 8B Instruct and Llama 3 to 70B Instruct models on code contests, Mini F2F, GSM 8K, and Math, generating 10,000 independent samples for each problem. For SWE Benchlight, we use the DeepSeek V2 Coder Instruct model, as this task requires a longer context than the Llama 3 models can handle. As is typical for solving SWE bench issues, we equip our language model with a software framework that helps it navigate and edit codebases, specifically using the open-source Moteless Tools library. It's important to note that solving a SWE bench issue involves a back-and-forth interaction between the language model and Moteless Tools. One sample or attempt for this benchmark refers to one complete multi-turn interaction. To keep costs down, we limit the number of attempts per issue to 250, with each attempt being independent. We present our results in a figure and also include the performance of GPT-4o on each task, as well as the best single-attempt performance for SWE Benchlight, which is achieved by Code Story Aid that combines GPT-4o and Claude 3.5 Sonnet. Across all 5 tasks, we observe that coverage steadily improves as we increase the sample budget. When all language models are given just one attempt, GPT-4o outperforms the Llama and DeepSeek models in every task. However, as the number of samples grows, all 3 of the weaker models surpass GPT-4o's performance from a single attempt. For SWE Benchlight, we successfully solve 56% of the problems, which is better than the single-attempt state-of-the-art performance of 43%. Section Summary. In this section, we explore how repeated sampling enhances coverage and success rates in pass-fail tasks across various datasets, including GSM 8K and Math, by generating multiple candidate solutions. Our findings indicate that while single-attempt models like GPT-4o initially outperform others, increasing the sample budget allows weaker models to surpass its performance, particularly in tasks with automatic verifiers. Section. Repeated sampling is effective across model sizes and families. In this section, we demonstrate that repeated sampling is effective across various model sizes and families. Our previous results indicated that repeated sampling enhances coverage, but we only illustrated this trend with 3 recent instruction-tuned models that have 8 billion parameters or more. Now, we expand our analysis to show that these trends are consistent across different model sizes, families, and levels of post-training. We include a wider range of models in our evaluation. Llama 3 models, which consist of Llama 3 to 8B, Llama 3 to 8B Instruct, and Llama 3 to 70B Instruct. Gemma models, including Gemma 2B and Gemma 7B, and Pythia models, ranging from Pythia 70M to Pythia 12B, totaling 8 models. To keep inference costs low, we focus our evaluation on the math and code contests datasets. Our findings, illustrated in a figure, show that coverage improves across nearly all models we tested, with smaller models experiencing some of the most significant increases in coverage when we apply repeated sampling. For instance, on the code contests dataset, the coverage for the Gemma 2B model jumps over 300 times, going from a pass rate of 0.02% to a pass rate of 7.1% when we look at the top 10,000 attempts. Similarly, when tackling math problems with the Pythia 160M model, coverage rises from a pass rate of 0.27% to 57% when considering the top 10,000 attempts. However, we note an exception with the Pythia family on the code contests dataset, where all Pythia models achieve zero coverage, even with a budget of 10,000 samples. We suspect this is because Pythia was trained on less coding-specific data compared to Llama and Gemma. Next, we discuss how repeated sampling can help balance performance and cost. One key takeaway from our results is that repeated sampling allows us to enhance the capabilities of a weaker model, enabling it to outperform single samples from stronger models. We illustrate that this amplification can be more cost-effective than using a stronger, pricier model, giving practitioners more flexibility in optimizing both performance and costs. We first consider floating point operations, FLOPs, as a cost metric, revisiting the Llama 3 results. We visualize coverage as a function of total inference FLOPs instead of the sample budget. Since Llama 3 models are dense transformers, where most parameters are involved in matrix multiplications, we approximate inference FLOPs using a specific formula. Our rescaled results for various tasks, including Mini F2F, code contests, math, and GSM 8K, are presented in a figure. Interestingly, the model that achieves the highest coverage varies depending on the compute budget and the task. For Mini F2F, GSM 8K, and math, the Llama 3 to 8B instruct model consistently outperforms the larger and more expensive 70B model when the FLOP budget is fixed. However, for code contests, the 70B model is generally more cost-effective. We acknowledge that looking at FLOPs alone can be a simplistic cost metric that overlooks other aspects of system efficiency. Specifically, repeated sampling can utilize high batch sizes and specialized optimizations that enhance system throughput compared to single-attempt inference workloads. We delve into this topic further in another section. We also analyze the dollar costs associated with repeated sampling when addressing issues in SWE Benchlight, using current API pricing. Keeping the agent framework constant, we compare making a single attempt per issue with Claude 3.5 Sonnet and GPT-4o against repeated sampling using DeepSeek V2 Coder Instruct. We present the average cost per issue and the issue resolution rate for each method in a table. Although the DeepSeek model is weaker than the GPT and Claude models, it is over 10 times cheaper. In this scenario, repeated sampling offers a more affordable option than paying a premium for access to stronger models while achieving a better issue resolution rate. Finally, we characterize the benefits of repeated sampling. The connection between a large language model's loss and its training compute has been well studied through training scaling laws. These laws have consistently held true across various scales, giving model developers confidence that significant investments in training will yield returns. Inspired by these scaling laws, we aim to better understand the relationship between coverage and the sample budget, presenting two notable observations. The relationship between coverage and the number of samples can often be modeled using an exponentiated power law, and for a specific task, the coverage curves of different models from the same family resemble S-curves with similar slopes but different horizontal offsets. We then develop a clear model for the relationship between coverage and the number of samples. The technical report for GPT-4 indicates that the relationship between a model's average pass rate on coding problems and its training compute can be effectively modeled using a power law. We adopt a similar function class, modeling the logarithm of coverage as a function of the number of samples. To directly predict coverage, we exponentiate both sides, leading us to our final model. We provide examples of fitted coverage curves in a figure, with additional curves available in the appendix. While these laws may not be as precise as training scaling laws, particularly on the Mini F2F math task, they offer promising early evidence that the advantages of inference scaling can be characterized. Section Summary. In this section, we demonstrate that repeated sampling significantly enhances coverage across various model sizes and families, with notable improvements observed in smaller models. We also highlight that repeated sampling can be a cost-effective strategy, allowing weaker models to outperform stronger ones in terms of coverage while reducing overall inference costs. Section: Similarities in coverage curves across models. In this section, we explore the similarities in coverage curves across different models. When we compare the coverage curves, which use a logarithmic scale on the x-axis, for various models within the same family tackling the same task, we notice that the S-curves we trace share the same slope but have distinct horizontal offsets. To delve deeper into this observation, we overlay the coverage curves of these models. We select a specific coverage value, which we call C, and shift each curve to the left in log space so that they all intersect at the point where the x value is 1 and the y value is c. This leftward shift corresponds to the logarithm of the inverse of the pass rate at c, where the pass rate is the closest whole number k that results in a pass rate equal to c. We choose c to be the highest pass rate at 1 across all models in the same family. These findings suggest that, for models within the same family, the increase in the log sample budget, or the multiplicative increase in the sample budget, required to enhance coverage from C to C, remains roughly constant. Next, we shift our focus to the importance of precision in repeated sampling. Until now, we have concentrated on measuring model coverage and the advantages of repeated sampling under ideal conditions, where we can always pinpoint the correct model samples. Now, we address the complementary issue of precision. Can we accurately identify the correct samples from a collection of model outputs? In our analysis, we evaluate two common verification methods, majority voting and reward model scoring, using the GSM-8K and math datasets. We also discuss potential challenges that arise when relying on unit tests to verify software programs. We find that among the 5 tasks we assess, only GSM-8K and math lack automated tools for verifying solutions. In this context, we evaluate 2 prevalent strategies for determining a final answer: calculating a majority vote from the samples and employing a reward model to score each sample. We test these methods on their effectiveness in identifying correct solutions from the 10,000 samples generated using Llama 3 to 8B Instruct and Llama 3 to 70B Instruct. We benchmark 3 approaches. 1. Majority vote. We select the most frequently occurring final answer. 2. Reward model plus best of n. We score each solution using a reward model and choose the answer from the highest scoring sample. 3. Reward model plus majority vote. We calculate a majority vote where each sample is weighted according to its reward model score. For our scoring, we utilize M-Llama 3 to 8 BV0.1, which currently holds the top reasoning score on the reward bench leaderboard among open-weight models. We present our findings as we increase the number of samples. Initially, the success rate rises with the number of samples for all 3 methods, but it levels off around 100 samples. In contrast, coverage continues to grow with the number of samples, surpassing 95%. The plateau in success rate for majority voting can be easily explained. As the number of samples increases, the distribution of votes for each answer stabilizes, leading to a plateau in success rate. For certain problems in GSM-8K and math, the probability of sampling correct solutions is very low, at 1% or less, which means they become a minority among the samples. As we gather more samples, we may encounter rare correct solutions for more problems, increasing coverage but not the success rate with majority voting. To fully leverage repeated sampling, our methods for identifying samples must effectively tackle these challenging cases and pinpoint rare, correct samples. Given the limited performance of the reward model, we question how difficult it is to verify a candidate solution. In the cases of GSM-8K and math, we only use the final answer of a sample to assess its correctness, ignoring the intermediate reasoning steps. If models produce nonsensical reasoning before arriving at a correct final answer, verification may be just as challenging as solving the problem itself. To investigate this, we manually evaluate 105 reasoning chains from correct solutions generated by Llama 3 to 8B Instruct for GSM-8K problems, and we report our findings. We discovered that over 90% of the reasoning chains we assessed are accurate, even for problems where correct answers are infrequently produced. These valid reasoning steps suggest that there is useful information for a verifier to utilize when identifying correct samples. Interestingly, during this evaluation, we also found one GSM-8K problem that has an incorrect ground truth answer. This particular problem is the only one for which Llama 3-70B instruct did not generate a correct sample across 10,000 attempts. Finally, we discussed the challenges faced by verifiers in software tasks. Software development tasks often find themselves in a middle ground regarding available verification tools. On one hand, the ability to execute and test code allows for a higher level of automatic verification compared to unstructured language tasks. However, tools like unit tests take a black box approach to verifying code and are not as thorough as methods like proof checkers. These limitations in the verification process can lead to false positives or negatives, which are crucial to consider when applying repeated sampling. We provide two examples of the imperfections we encountered in software verification while generating our results. Section Summary. In this section, we observe that models from the same family exhibit similar coverage curves with consistent slopes but different horizontal offsets, indicating a constant increase in sample budget needed for coverage improvement. We also evaluate common verification methods for identifying correct model samples, finding that while coverage increases with more samples, the success rate plateaus due to the rarity of correct solutions, highlighting the challenges in effectively verifying candidate solutions in tasks like GSM-8K and math. Section: Flaky tests in SWE Benchlight. In this section, we discuss our findings from SWE Benchlight, where we discovered that 11.3% of the problems have flaky test suites. These flaky tests do not consistently yield the same results when we run them on the same candidate solution. Sometimes, they even incorrectly label the correct solutions in the dataset as wrong. Additionally, for some problems, the test suites can behave unpredictably based on the candidate solution. For instance, two issues in SWE Benchlight involve working with Python sets, which do not have a specific order. The correct solutions for these problems explicitly arrange the items in a certain order and consistently pass the tests. However, some solutions generated by models do not follow this ordering, leading to situations where they pass the tests on some attempts but fail on others. We have included a list of all the problem IDs with flaky tests in the appendix. We also analyzed our results from SWE Benchlight after removing the problematic issues and found that the outcomes were similar to our evaluations of the entire dataset. Next, we turn to the code contests dataset. Each problem in this dataset comes with a set of input-output test cases designed to check the correctness of solutions. These test cases are more thorough than those from earlier benchmarks like apps, which helps reduce the number of false positives, solutions that pass all tests but do not actually solve the problem. However, the way the code contests test suites are constructed can lead to false negatives, where correct solutions fail the tests. In some cases, the problem descriptions allow for multiple valid outputs for a given input, but the test cases only accept one specific correct output. Moreover, many of the test cases in code contests are created by modifying original test cases, which can sometimes result in inputs that do not meet the problem's requirements. For example, an input that should be a positive integer being 0. These flawed test cases can cause different correct solutions to behave inconsistently. We evaluated how often these issues occur by running the test suites on the correct solutions provided by code contests. Out of the 122 problems in our test set with Python 3 solutions, we found that 35 problems had correct solutions that did not pass the corresponding tests. Since we do not allow models to see all the test cases and their specific requirements, generating a solution that is both correct and meets the test criteria involves an element of chance. In our discussion of the work, we explore how repeated sampling can enhance model performance during inference. We found that across various models and tasks, repeated sampling can significantly increase the number of problems solved with any generated sample. When we can identify correct solutions using automatic verification tools or other methods, repeated sampling can boost the model's capabilities during inference. This means that a weaker model, when combined with many samples, can perform better and be more cost-effective than using fewer attempts from a stronger, more expensive model. We also looked into ways to improve repeated sampling. In our experiments, we only tested a basic version of repeated sampling where all attempts for a problem are generated independently using the same prompt and settings. We believe this approach can be refined to enhance performance, particularly in the following areas. 1. Solution diversity. Currently, we use a positive sampling temperature as the only way to create diversity among samples. We think that combining this method with other higher-level strategies could further increase diversity. For example, AlphaCode uses different metadata tags to condition various samples. 2. Multi-turn interactions. Although we have access to automatic verification tools for solving code contests and mini F2F problems, we only use a single-turn setup where models generate a solution without the chance to refine it. Providing models with feedback from these tools could improve the quality of the solutions. We are interested in the trade-offs of multi-turn interactions, as each attempt may become more costly but also more likely to succeed. 3. Learning from previous attempts. Right now, our experiments treat each attempt as completely separate. Having access to previous samples, especially if verification tools can provide feedback on them, could be beneficial for generating future attempts. 4. Repeated sampling and inference systems. Repeated sampling represents a different type of workload for large language model (LLM) inference compared to serving chatbot requests. In production chatbot settings, there is a focus on low response times, which can limit the batch size and reduce hardware efficiency. In contrast, when we sample many completions from a single prompt, we can prioritize overall throughput and maximize hardware use. Additionally, repeated sampling can take advantage of specialized optimizations that exploit similarities in prompts across sequences. Therefore, repeated sampling can be done at a lower cost than simply making many parallel requests to a chatbot-oriented API. This cost efficiency can further encourage the choice to sample multiple times from a less expensive model rather than fewer times from a pricier one. 5. Verifiers. Our findings highlight the need to enhance sample verification methods, especially when automatic tools are not available. Equipping models with the ability to evaluate their own outputs will allow us to scale repeated sampling to many more tasks. We are particularly interested in applying repeated sampling to unstructured tasks like creative writing, which may require a more subjective comparison between different samples than the pass-fail tasks we have focused on. Another approach to developing model-based verifiers is to create converters that can make unstructured tasks verifiable, such as formalizing an informal math statement into a formal language like Lean, allowing proof checkers to be used. Section Summary. In this section, we identify that 11.3% of problems in SWE Benchlight exhibit flaky test suites that yield inconsistent results, sometimes misclassifying correct solutions, while in the code contests dataset, we find that certain test cases can lead to false negatives due to their restrictive nature and malformed inputs. We also discuss the potential of repeated sampling to enhance model performance, emphasizing the need for improved solution diversity, multi-turn interactions, and better verification methods to maximize the effectiveness of this approach. Section: Related work. In this section, we explore various methods that enhance inference computation in deep learning. We note that techniques which add extra computation during inference have shown success in many areas. For instance, in different gaming environments, top methods utilize inference time searches that evaluate numerous potential future game states before making a move. We also find that tree-based methods can work well with large language models, LLMs, enabling better planning and exploration of different strategies. Another way to boost LLM inference is by allowing models to take time to think through a problem before arriving at a solution. Additionally, we can combine multiple models at inference time to leverage their strengths. Another interesting approach involves having LLMs critique and improve their own responses. We also discuss the benefits of repeated sampling, which previous studies have shown can enhance LLM performance across various fields. A particularly effective application is in coding, where performance improves significantly with up to 1 million samples, especially since verification tools like unit tests can automatically evaluate each candidate solution. Recent findings indicate that repeated sampling is also useful for solving puzzles in the ARC challenge, showing a log linear improvement as the number of samples increases. In chat applications, combining repeated sampling with a best of n ranking and a reward model can yield better results than simply selecting one response. In areas lacking automatic verification tools, using majority voting or a trained model-based verifier can lead to better outcomes in reasoning tasks compared to relying on a single sample. Our work aligns with findings that suggest using the best available sample can enhance LLM performance in chat, math, and coding tasks, with improvements noted up to a maximum of 128 samples. We then turn to scaling laws, which help us understand how scaling impacts model performance, guiding us in resource allocation. Research on LLM training reveals a power law relationship between loss and the amount of training computation, providing insights into the optimal model and dataset size for a given compute budget. We also observe scaling laws in the context of the board game Hex, where performance scales predictably with model size and problem difficulty. Notably, performance also improves with the amount of compute used during test-time tree searches. Recent studies have shown that augmenting LLMs with external retrieval datasets leads to smooth performance scaling in retrieval tasks as the size of the retrieval corpus increases. In our acknowledgements, we express our gratitude to Together AI for partially funding the compute resources for this project, and we thank Rahul Chalamala and Ben Atiwaratkun for their assistance in managing this infrastructure. We appreciate John Yang's advice and support during our SWE bench experiments. We are also thankful to Mei Chen, Neil Guha, Quinn McIntyre, John Saad Falcon, and Benjamin Spector for their valuable discussions and feedback throughout this project. We acknowledge the support from various organizations, including NIH, NSF, USDEVCOMARL, ONR, Stanford High, and several industry partners. The U.S. government is permitted to reproduce and distribute this work for governmental purposes, regardless of any copyright notices. The opinions and conclusions expressed in this material are solely those of the authors and do not necessarily reflect the views or endorsements of NIH, ONR, or the U.S. government. Finally, we completed this work with the support of the Clarendon Fund scholarships.